And so some properties of gases or characteristics of gases is that unlike liquids and solids, it conforms to the shape of the container and fills it. So whatever container you use is going to fill the volume of that container, and whatever shape that container is, it's going to assume that shape of the container. Another important aspect of gases is that they're very far apart and move in random straight line fashion. Now, some interesting things about gases that we're going to touch on in this lecture is how the volume of a gas is affected by pressure, because pressure and volume are two quantities of a gas that you can measure. So we're going to look at the relationship between the two. So as we decrease volume, what happens to pressure, vice versa. Another thing that gases, a characteristic of gas, is how volume is affected by temperature. And so we're going to look at the relationship between volume and temperature and show how they're affected by one another. Gases flow freely and they have low densities. We're talking gram per liter, whereas solids and liquids are grams per milliliter, and they form homogeneous solutions in any proportion. So anytime you have a mixture of gases, they form a homogeneous solution. So we're going to look at some of these different aspects of gases in this lecture. Now, as for the properties of gases, we mentioned pressure, and the kind of the chemical definition, if you want to say it like that, is for pressure is the when the gas molecules collide on the walls of the container. So as the gas molecule is moving, it has a force, it collides with a certain area on the container. That's where we get gas pressure, and the mathematical equation is force per area. So as you can imagine, as you decrease the volume, then there's less space for these molecules to move. So therefore, you're going to increase its pressure, because now they're going to be hitting the walls of the container more often. So the more often they hit the walls of the container, the higher the pressure is. Now, there are two types of apparatuses that we can use to measure pressure. One is a barometer, which measures atmospheric pressure, and it looks something like this contraption down here. So you have a tube that has a graduated scale, and then you have a pool of mercury. As the atmospheric pressure pushes down on the pool of mercury, it causes the mercury to rise in the tube. And these little graduations are typically millimeters or could be inches, and that's where we get the pressure from. For example, millimeters of mercury is how high the mercury has risen. Now, for experiments, we typically use a manometer to measure the gas pressure, and it's this contraption over here to the right. We have a closed end and an open end manometer. So for a closed end, we have an initial height. As the reaction occurs, it produces a gas and pushes the liquid up. So the difference between the initial and final height can tell you the pressure. Same thing with an open one, but with an open one, it's exposed to the atmosphere. So again, you have the atmospheric pressure pushing down. As you do your reaction, gas is produced and pushes the liquid up, and the difference in height can give you the pressure of the gas. So with an open manometer, the pressure of the gas is equal to the atmospheric pressure and the pressure of the height. Whereas a closed end, the pressure of the gas is equal to the pressure of the height. So you would actually measure this and know how many millimeters of mercury or inches of mercury you have. Now, there are many different units of pressure that we use. The SI unit, which is a derived unit, is Pascal, and a Pascal is a Newton meter squared, because Newton is the SI unit for force, and meter squared is the SI unit for area. So force per area gives us pressure. And so SI unit is Pascal for pressure. Now, one type of unit we use quite often is atmospheres, ATMs. As you can see, this is the average atmospheric pressure measured at sea level. And we can convert between atmospheres and pascals and even kilopascals. And again, this is the atmospheric pressure measured at 0 degrees Celsius. The next common unit that we use is millimeters of mercury. And this term comes from measuring the height that the mercury has risen in millimeters. So each one of these graduations is a millimeter. So as it rises, we measure the height in millimeters of mercury, and that's where we get the unit millimeters of mercury from. Now, technically, you're supposed to use millimeters of mercury only at 0 degrees Celsius. If it's at any other temperature, we use the term torr to represent millimeters of mercury. But they're exactly the same unit, torr and millimeters of mercury, just at different temperatures. And here we see that 1 atmosphere is equal to 760 millimeters of mercury. And this is one important conversion that you need to remember. And this is an exact conversion. So these are by far the two most common units of pressure that we use. We use atmospheres and we use millimeters of mercury. Some less common ones is a bar, and a bar is 100 kilopascals. And maybe if you've ever put air in your tire, you put in PSI, which is pounds per square inch. And this is how we can convert between PSI and ATM. So needless to say, there are lots of different units of pressure. The two most common ones that we use are atmospheres and millimeters of mercury. So as I mentioned earlier, there are 4 properties of a gas, or there are 4 properties of a gas we can measure. So we've mentioned pressure. With pressure, generally we do it in measurements of millimeters of mercury and torr, but there are certain calculations in which it needs to be in atmospheres. And I'll let you know which equation, when used, pressure has to be in ATM. So there are certain equations that pressure has to be in atmospheres. For a gas with temperature, typically we measure in degrees Celsius. Now for all calculations, it has to be in Kelvin. So that's all calculations needs to be in Kelvin. So any calculation you do in this chapter involving gases need to be in Kelvin. And the way we convert to Kelvin, Kelvin equals 273.15 plus degrees C. Now with volume, generally we measure in milliliters, or you can measure in liters as well. But for some calculations, volume has to be in liters. And I'll let you know which equations that you need to have volume in liters for. And then lastly, the amounts. Typically, we measure this in grams, but for all calculations, we have to do in moles. We have to convert grams to moles. Now, all of these different properties or variables that describe a gas are interdependent, so they all affect one another. So we're going to look at how pressure is affected by volume, how temperature is affected by volume, vice versa, how a volume is affected by amount, and how pressure and temperature are affected as well. And so these come up with the individual gas laws, where we have 2 of these are changing and 2 other properties are held constant. So for example, when we're looking at pressure and volume, temperature and moles are constant, so they don't change. Now, for most of this, for most of the time we're talking about gases, we think of them as behaving as ideal gases. And so toward the end of the lectures on gases, we'll talk about a real gas and how it deviates. But for the majority of this chapter on gases, we'll be looking at these gases as ideal gases. So what does ideal gas mean? It means when you plot, for example, volume versus temperature, you get a linear relationship. If you plot, any of the properties versus one another, you get a linear relationship between the two. So that's the behavior of an ideal gas. Well, as you can imagine, no ideal gas exists. However, these gases here, such as nitrogen, oxygen, hydrogen, and the noble gases, get pretty close to being ideal at ordinary temperature and pressure. So when we talk about a gas laws, we're going to be talking about them with respect to a gas behaving like an ideal gas. And again, at the end of this chapter, we'll talk about real gases. So what we're going to do is we're going to go through each law, and then at the end, we're going to work out problems involving each of the different laws. So the first law is Boyle's law, and Boyle's law relates pressure and volume at constant temperature and moles. So whenever you're reading a problem and it involves Boyle's law, you'll notice that pressure and volume are changing, but the temperature and moles are held constant. And when we hold temperature and moles constant, we come up with this equation here: V equals K over P at constant temperature and moles. And so what does this mean? It means if you plot volume versus 1 over P, you're going to get a linear relationship. Now, if you know the pressure and volume, and you're going to change the pressure and want to calculate the new volume, we would use this equation here. So again, this equation is useful when we know the pressure and volume of a gas, and we want to say increase the pressure, we can calculate the new volume. And so over here in the pictures, the top picture is Mr. Boyle. Again, this was all around, if you want to imagine, the somewhere between the 16th and or the 17th and early 19th century. So in that time frame is when these laws were coming about. And the bottom picture is an example of Boyle's law. So here this person is scuba diving. As they descend in the water, the pressure increases, therefore the volume decreases. And so this is the only law where the two are inversely related. So as you increase volume, you're going to decrease pressure and vice versa. And again, this is the only law that is inversely related. And so in this little picture here, what we're having is these weights signify pressure, and then this signifies the volume of the container. Now, if you count the number of spheres, it's constant. And since it's a blue color, it means constant temperature as well. So as we increase the pressure, so here we went from 1 pressure to doubling it. So when we double the pressure, the volume decreases to a half of its original value. And then when we quadruple the pressure, the volume increases to 1/4 its original value. So as you increase pressure, the volume decreases by the same factor. And so this is Boyle's law. Again, pressure and volume. Next, we have Charles's law. Now, Charles's law looks at 2 other properties, looks at volume and temperature. And this is at constant pressure moles. So the pressure is not changing. the moles are not changing. And so when we do that, we get a equation like this: V equals KT at constant pressure and moles. So if you were to plot volume of the gas versus temperature at constant pressure and moles, you get a linear relationship. So as volume increases, temperature increases. And so the equation we can use to calculate, given the volume and temperature, if we increase the volume, we can calculate the new temperature. But here, temperature has to be in Kelvin. And this is a very common mistake. Students forget to convert it to Kelvin units. And the reason it needs to be converted to Kelvin is because Kelvin is an absolute temperature, which means it cannot be negative. If you have it in degrees Celsius, you could have negative temperature, which means the volume could be negative. And what does negative volume mean? Exactly, nothing. So now if we look at the cartoon, or the picture again, the top picture is a picture of Mr. Charles. The bottom picture, we have a balloon. It has a fixed amount of gas in it with a certain pressure. We put the balloon in liquid nitrogen. Since the temperature decreases, the volume decreases as well. When you take it out, it looks all shriveled up. Now, if you allow it to heat back up, you'll actually see the balloon start to expand again. Now, if you wanted to try this at home, if you blow up a balloon and you don't have, of course, liquid nitrogen around your house, but you have a freezer, you can stick it in the back of the freezer, leave it there for a couple of weeks or a month. And if you measure, you'll notice that the volume has decreased, because as the temperature of the gas in the balloon decreases, the volume of the balloon decreases as well. So another law that combines Boyle's and Charles' law is called Gay-Lussac's law. And in Gay-Lussac's law, it relates temperature and pressure at constant volume and moles. And so if we look at the relationship between the two, if we have pressure and temperature, we get this expression P equals KT at constant volume and moles. So if we were to plot pressure versus temperature, we would get a linear relationship. And by the way, the slope of this line would equal K. So if you plot pressure and temperature, again, temperature has to be in Kelvin. Always in Kelvin. You get a linear relationship with pressure. Now, if we know the pressure and temperature of a gas and we want to increase the temperature, we can calculate the new pressure by using this equation here. So on this little cartoon in the middle, the man or the men represent pressure. The candles represent temperature. So when we have half a man, we have half a temperature. If we double the man, we double the temperature. So now we have two halves, so we have two halves of candle. If we quadruple the number of half men from the beginning, we quadruple the number of candles. So this is the relationship between pressure and temperature. As you increase pressure, temperature is also going to increase. Kind of a couple of examples of this. You can take a hot can, you heat it up to very high temperature, you put it into the ice water, and since there's such a dramatic change in temperature, the pressure decreases so rapidly that it crushes the can. Likewise, if you ever used one of those cans of air that you spray and clean the computer with or whatnot, you know over time that the can starts to frost up, because as you're spraying the can of air, you're decreasing the pressure inside, and as you decrease the pressure inside, you decrease its temperature, and that's why the can frost up. Another good real life example of this is if you've ever been, it's a cold morning, you go to start your car, you say, hey, there's a tire light on a very cold morning. What's happening is that your tire, which is a constant volume and amount of gas, since the temperature got so cold outside that it decreased your pressure in your tire just enough to trip the tire sensor in your car. So the best thing to do is just go and put some more air in it to rise it above that sensor limit. And that's an example of Gay-Lussac's law. So lots of different examples of this. So we looked at Boyle's law, which is pressure and volume, Charles's law, which is volume and temperature, Gay-Lussac's law, which is pressure and temperature. So what we're doing again in all of these, we're looking at two properties, how they're interdependent, while the other two properties are held constant. Now, if we combine Boyle's and Charles's law, we get what's called the combined gas law. And so with the combined gas law, we get this expression here, V equals KT over P. And so with the combined gas law, the only thing that's constant is the moles of gas. And so again, with temperature, it needs to be in Kelvin. And if we know the pressure, volume, and temperature of a gas, and we want to change, say, the pressure and temperature, we can calculate the new volume by using this equation here. And this is called the combined gas law equation. It takes Boyle's and Charles's law and puts them together. Now, one type of property we haven't talked about is amounts. And so volume is affected by the amount of gas at constant pressure and temperature. And this is referred to as Avogadro's law. Same Avogadro who looked at Avogadro's number, or who came up with Avogadro, or who's the number Avogadro, the number is named by, I should say. And just to let you know, October 23rd is Mole Day. So on that day, if we were at school, typically the chemistry clubs would sell little mole keychains or mole t-shirts for that day. So again, that's October 23rd, 1023. And so with volume, it is directly related to amounts. So if we increase the amount of a gas at constant pressure and temperature, we're going to increase its volume. And so if we were to plot volume versus moles, we would get a linear relationship. Remember, the slope equals K. Now, if we know the volume in moles of our gas and we want to add more gas to it, we can use this equation to calculate the new volume of gas at constant pressure and temperature. So now this shows the relationship between the amount and volume of a gas. One last thing we have to look at when talking about gases is typically in some problems it says, this gas was collected at standard conditions, or this experiment was conducted at the standard conditions for a gas. And so what is the standard conditions of a gas are? The standard temperature is 0 degrees Celsius, 273 Kelvin. The standard pressure is 1 atmosphere, 760 millimeters of mercury, and this is referred to as STP. So if you're reading a problem and it says the gases or the gas was collected at STP, this is the temperature and pressure of the gas. Now, at this standard of temperature and pressure, if you have 1 mole of gas, it occupies 22.4 liters. So what does that mean? That means if you have 2 moles of gas at STP, the volume would be 44.8 liters. And if you had 3 moles of gas at STP, the volume would equal 67.2 liters. And so the molar volume, again, is the volume occupied by 1 mole of gas at STP. But if you have more than 1 mole of gas at STP, you just simply multiply the number of moles by the molar volume to get the volume of your gas at STP. Again, you can only do this at standard temperature and pressure. So now if we take Boyle's law, we take Charles's law, we take Avogadro's law, and we combine them all, we get what's called the ideal gas law. And so the ideal gas law is what you can use to derive all of the other individual gas laws. And so with the ideal gas law, we have pressure for P, volume for V, N is of course the number of moles, and T is temperature. Now, when we use the ideal gas law, pressure has to be in atmospheres, always. Volume has to be in liters. N, of course, is moles. And temperature has to be in Kelvin. These are musts when using the gas law, because if you notice here, we have this R here, which is the gas constant. And the gas constant is in units of atmosphere liter per mole Kelvin. So since our gas constant is in these units, this is why we have to have the pressure, volume, moles, and temperature in a particular unit. And the way they get the gas constant is they take all the standard conditions that we just mentioned in a previous slide, you plug them in and you solve for R, and you get this. So pressure is 1 atmosphere, volume 273 Kelvin, moles is 1, excuse me, volume is 22.4, moles is 1, temperature is 273. When you work that out, you get 0.0821 atmospheres liter per mole Kelvin. And I'll show you when do we use the ideal gas law and when do we use the individual gas laws.
So let's continue. So now we have lots of different problems we're going to look at. So in number 1, we have a 2.5 liters of a gas, changes in pressure from 100 to 40 kilopascals. What's the new volume if the temperature is constant? And so when we look at this problem, what we notice is that it gives us the volume and it gives us pressure, and we want to find the new volume. And it says temperature is held constant. Secondly, since it didn't mention anything about moles, you can assume that moles is held constant as well. So what we have is pressure and volume are changing. And temperature and moles are constant. And so this tells us we're going to be using the equation for Boyle's law. P1 V1 equals P2 V2. Now when we do these types of problems, I like to do a little chart here. So we have our pressure, we have our volume, initial, or you could say 1, final, or you can say 2, and the prediction. So we're going to predict what happens. So the pressure is given to us. We start with 100 kilopascals. That's our initial pressure. Our final pressure is 40 kilopascals. Now for the volume, our initial volume is 2.5 liters. We don't know our final volume right now. So that's what we're looking for in this problem. Now with Boyle's law, volume and pressure can be in any unit. So as long as both pressures are in the same unit, both volumes are in the same unit, that's fine. So what we see here is that pressure decreases. So if pressure decreases, we predict that volume should increase because this is Boyle's law. They're inversely related. So our volume should be greater than 2.5 liters. So now when we set this up, and we can solve for V2. And we get 6.25 liters. Not 6, but hold on. Let me do this back. Yeah, 6.25. So as we predicted, volume did increase. If our volume decreased, that would raise a flag and say, hey, we might have done something wrong. Now moving on to the second example, here we have a sample of gas occupies 6.8 liters at 327 degrees Celsius. What will its new volume be at 27 degrees Celsius if pressure does not change? So in this example, volume and temperature are changing. Pressure and moles are constant. So if you look back at our individual gas laws, we'll be using Charles's law, which is V1 over T1 equals V2 over T2. But now, before you start jumping and plugging in numbers, we have to convert temperature to Kelvin. So now I'm going to draw another chart here so we can observe what's happening. So we have volume, temperature, initial, final, prediction. So our initial volume is given to us, 6.8 liters. Now for the temperature, is 327 degrees Celsius. Now to convert this to Kelvin, we have to add 273.15 to it. So make sure you convert it to Kelvin. Then we want to decrease the temperature to 27 degrees Celsius, which is, if we convert this to Kelvin, 300.15 Kelvin. Again, I get Kelvin by adding 273.15 to the degrees Celsius. So now we do our prediction. You see that the temperature decreased, so our volume should also decrease as well. So now we set up the equation. Move some stuff around. Again, if we did this correctly, our volume should be less than 6.8. And we get a volume of 3.4 liters. So as we predicted, volume should decrease, and it did. So notice that in each one of these examples, some properties are changing, some are held constant. That's an indication that we have to use one of the individual gas laws. So we notice that properties are changing, initial and final, some are held constant. So that's an indication that we have to use individual gas laws to solve for it. Now in the third example, we have a sample of gas that occupies 8.75 liters, 250 degrees Celsius, and 780 torr. We want to calculate its volume when we change the temperature to 60 degrees Celsius and 960 torr. So notice here that 3 of the properties are changing and 1 is held constant. The only thing that's held constant is moles, because it doesn't give us any information about moles, it just says a sample of gas, so we can assume moles are constant. So what we're going to use is what's called the combined gas law. And this is because 3 of the properties are changing, 1 is held constant. That's P1V1, T1 equals P2 V2 over T2. So now if we draw our chart, so you're going to have pressure, volume, and temperature. We have the initial, final, prediction. So the pressure, it doesn't matter what units they're in, as long as they're in the same unit. So we know the initial and final pressure. Now for volume, we know the initial volume. We don't know the final volume, that's what we're looking for. For temperature, we have 250 degrees C. We got to convert that to Kelvin by adding 273.15. And we know our final temperature, 60 degrees Celsius. And we convert that to Kelvin. We get 333.15 Kelvin. So now for our predictions, let's see if we can make a prediction, or is it inconclusive? We see that pressure increases and temperature decreases. So what we know is that when pressure increases, volume tends to decrease. And if temperature decreases, if we're looking at Charles's law, volume tends to decrease. Now notice how both of these are pointing to volume should decrease. So since both of them are pointing at the same type of prediction, we can predict that volume should decrease. And so our volume should be less than 8.75 liters. So now we work this out. Now I'm going to move some stuff around. We got to get V2 by itself, so I'm going to multiply both sides by 333 and divide both sides by 960. And I did this to get V2 by itself. And now we can solve for V2. And I get 4.53 liters. Let me double check. Yeah, so that's the volume of the gas when we decrease the temperature and increase the pressure at constant moles. So just like we predicted, it decreased as well. So in example 4, we have a sample of gas at a pressure of 590 torr at 127 degrees Celsius. What will its pressure be at 95 degrees Celsius if the volume does not change? So in this example, we see that we have an initial pressure, an initial temperature. It gives us a final temperature, and it says what's the final pressure going to be. It states that volume does not change, meaning volume is constant. It doesn't mention anything about the moles, so we can assume moles are constant as well. So in this one, we have volume and moles constant. And that means pressure and temperature are changing. So this means we're going to use Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So here we have pressure and temperature. So again, pressure, it doesn't matter the units. It can be in any unit as long as they're both consistent. So we can leave this in torr. Now the temperature needs to be in Kelvin. So to convert that, we add 273.15, and we get 300.15 Kelvin. And if the final temperature is 95 degrees Celsius, and we get 368.15 Kelvin. Now we look at Gay-Lussac's law. Remember, pressure and temperature are directly related. So here you see temperature increases. So if temperature increases, pressure is going to increase as well. So our final pressure should be greater than 590 torr. Now we can set it up to solve for the new pressure. Now to get P2 by itself, we have to multiply both sides by the 368.15. And now we get P2 by itself. And we get a pressure of 724 torr. So just like we predicted, pressure should increase. Our pressure did increase. So that means we're on the right track. Now, if you did this and your pressure decreased, that should raise a red flag and say, hey, we've done something wrong in our calculation. Now, moving to number 5, we have a balloon contains 5.1 liters of helium at 24 degrees Celsius and 101.5 kilopascals. If we heat the balloon to 35 degrees Celsius and it has a pressure of 102.8 kilopascals, what's its new volume? So when you read this, you notice that we see 3 properties of gas changing. It's given us the volume, temperature, and pressure. And we're changing the temperature and pressure, and it wants to know what's the new volume of the gas. So since the only thing held constant is moles, this tells us that we're going to use the combined gas law. And the way we know that is because 3 of the properties are changing, only moles is held constant. That's P1 V1 for T1 equals P2 V2 over T2. So now if we set up our table, so notice out of doing all these examples, we're always having an initial and final.
Mr. Oman.
Thank you. I got it. Yeah. Thanks. Let's see. And predict. We only just have one more example, just these 2 left. So our pressure is 101.5 kilopascals. And again, pressure can be in any unit. Our volume, 5.41 liters. And temperature, 24 degrees C. And let's see, we had 273. What is that? 297.15. Is that right? 293. Yep. Kelvin. In our final state, we have 102.8 kilopascals. Temperature is 35 degrees Celsius. 308.15 Kelvin. So now let's see if we can make any prediction. So we see pressure increases. So if pressure increases, volume should decrease according to Boyle's law. And here we see temperature increases. And according to Charles's law, volume should increase. So here in this case, it's inconclusive because they're both saying opposite things. So now when we set this up, and we can solve for V2. Now notice to get V2 by itself, we have to divide both sides by 102.8 and multiply both sides by 308.15. Now you can do this in different ways. I'm just showing you how we move everything to one side. And we get 5.54 liters. Let me double check. .52 this time, somewhere around in there as well. Check one more time. Yeah, 5.54. Should be a 4. Now just to do one more example here, I just want to show you when did we use the ideal gas law versus the individual gas laws. So here we have this underground cavern has 2.24 times 10 to the 6 liters of methane gas at a pressure of 1500 kilopascals and a temperature of 42 degrees Celsius. How many moles of methane does this cavern contain? So in this problem, which is different from the other problems, you notice that nothing is changing. Here it gives us the volume, it gives us the pressure, and it gives us the temperature, and it just wants to know how many moles is in this sample of gas. And so when it just gives you 3 properties and asks you to calculate the 4th, we're going to be using the ideal gas equation, PV equals nRT, and in this case we're solving for moles, so it'll be PV divided by RT. Now R is a gas constant, which doesn't change. Pressure, remember, has to be in atmospheres. And so to convert pressure from kilopascals to atmospheres, we have to divide by, it's 101.3 or 5, I believe, kilopascals in 1 atmosphere. And this will tell us the number of atmospheres in the pressure. Because again, pressure always has to be in, or is it 101.3? I think it's 101.3. Because pressure always has to be in atmospheres. So we get 14.81. So you have to make sure to convert it pressure to atmospheres. Volume 2.24 times 10 to the 6. Now this is in liters. It's good. And then temperature needs to be converted to Kelvin. $315.15. Okay. Now that we have all the units in the, or all the values in the right units, we can plug it in and solve for moles. So again, notice how this is different. Nothing is changing. We simply give you 3 properties and want to know what the value of the 4th property is. And we get 1.29. 6 e to the 6 moles of methane. Let me double check. So that's how many moles of methane are in this cavern. Now to know how many grams of methane, we simply find the molar mass of methane, which is 16 grams per mole. And remember, mass is moles times molar mass. And that gives us the grams. And we get 2.06 e to the 7th grams. Just to summarize again, when 2 properties or 3 properties are changing, you have to use the individual gas laws. When you're just given 3 properties and asked to calculate the 4th property, that's when you use the ideal gas equation. Okay, just one quick correction that I saw in this problem I did, number 4. Instead of 300.15 Kelvin, it should be 400.15 Kelvin. That's a mistake on my part. So now if we change this to 400.15 Kelvin, you see that temperature decreased. So since temperature decreased, pressure should also decrease. So now we have to replace this with 400.15. And so when we do that, our pressure should be less than 590 torr. And we get 543 torr. So that's the new pressure when we decrease the temperature. So again, just a simple mistake. I forgot to add 100 to the Kelvin. So it should be initial temperature should be 400.15 Kelvin. it goes down to 368.15 Kelvin. So when we plug that in and we solve for the new pressure, it should be less than 590. And we get 543 torque. So again, the main thing here is that when properties are changing for initial final state, we're going to be using individual gas laws. When we're just given 3 of the properties, asked to calculate the 4th property, that's when we use the ideal gas equation. So until next time, Dr. Armand signing off.